Welcome to the lesson on irrational numbers. At the end of this lesson, you will be able to define irrational numbers and represent irrational numbers on a number line. You must have guessed that these numbers are not rational numbers. Such numbers are called irrational numbers. To understand an irrational number, we'll recall the definition of rational numbers. Numbers that can be written in the form of p upon q, where p and q are both integers and q is not equal to 0, are called rational numbers. The collection of rational numbers is denoted with the letter q. Now, let's consider the numbers that are remaining. Can these numbers be expressed in the form of p upon q? No, none of these numbers can be written in the form of p upon q. Let's read out the formal definition of irrational numbers. Numbers which cannot be expressed in the form of p upon q, where p and q are integers and q is not equal to 0, are called irrational numbers. The collection of irrational numbers is denoted with q bar. Next, let's see where these numbers can be placed on the number line. We'll begin with the representation of square root 2 on the number line. The method that we are about to discuss was discovered by the Greeks. Let's see how they represented these numbers on the number line. Consider a right-angled triangle OAB. Its base OA and height AB is 1 unit each. Here we need to find the hypotenuse OB. Recall the Pythagoras theorem that states, in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Applying this theorem to triangle OAB, we get this equation. On substituting the values of OA and AB, we get OB square is equal to 2. Therefore, OB is equal to the square root of 2. If we represent OB on the number line, it means we are representing the value of the square root of 2. The vertex O of the triangle must coincide with the 0 on the number line. The vertex A will coincide with 1 on the number line. In order to represent the square root of 2 on the number line, mark the length OB with the help of a compass. Then take of 3. With O as the center, mark the length of OD with the compass you're learning. Real numbers and explain their decimal expansion. You will also be able to express the decimal expansion of a rational number in the form of p divided by q and determine an irrational number q, where q is not equal to 0. The collection divided by 7 are some examples of rational numbers. These numbers are called irrational numbers. Here are a few examples of irrational numbers. You note that the square root of any prime number, it is represented by the capital letter R. Let's observe the divisions carefully. Here are the conclusions based on the observations. The remainders become 0 after a certain stage or repeat themselves. If the remainders repeat, then the digits in the quotient are also repeated. Here, two cases arise. On solving 15 divided by 8, the remainder becomes 0 after some steps, and its decimal expansion is equal to 1.875, since the decimal expansion of the rational number is the quotient of division. In this case, the decimal expansion terminates after certain steps. The decimal expansion of such numbers is called terminating. In the second and third case, the remainder never becomes 0. In these divisions, the remainders repeat after a definite stage. Here, these blocks of digits repeat in the quotient of the divisions. We say that these expansions are non-terminating recurring. Commonly, we represent the recurring digits in the quotient with a bar on top of it. We read this as 0.6 bar. All rational numbers can be expressed either as terminating decimal expansion or non-terminating recurring decimal expansion. Let's now express a terminating or non-terminating recurring decimal in the form of p divided by q, where p and q are integers and q is not equal to 0. Let's begin with the first example. Here the decimal expansion is terminating. Converting a terminating decimal into a fraction is very simple. Multiply and divide the decimal by 1000 since there are 3 digits after the decimal point. The obtained fraction is a rational number. Now, we'll consider the non-terminating recurring decimal 0.6 bar. Consider a rational number x. The decimal expansion of x is 0.6 bar. This can also be expressed as 0.666 and so on. Here, only one digit 6 is repeating itself. So we multiply the equation with 10. The right-hand side of this equation can be expressed as the sum of an integer and a decimal. The right-hand side of this equation is now equal to 6 plus x. Let's solve this equation. We get x equal to 2 divided by 3, which is a rational number. Similarly, every non-terminating recurring decimal expansion can be expressed in the basic form of a rational number. On summarizing, we can say the decimal expansion of every rational number is either terminating or non-terminating recurring. On the other hand, the decimal expansion of an irrational number is non-terminating, non-recurring. Here is an example of an irrational number. Some more examples of irrational numbers are the square root of 2 and pi. There are infinitely many rational and irrational numbers. Can you find an irrational number between two rational numbers? Let's try. Consider two rational numbers, 1 divided by 3 and 2 divided by 3. First, we'll find the decimal expansion of the first rational number. Thus, 1 divided by 3 is equal to 0.333 and so on. Next, let's find the decimal expansion of the second rational number, 2 divided by 3. 2 divided by 3 is equal to 0.666 and so on. Can you find a number which is non-terminating, non-recurring between the two decimal expansions? We can find a number of this pattern. Here, we have put increasing number of zeros between two consecutive 34s. This number is non-terminating and non-recurring. Similarly, we can find many such numbers. We have seen that a real number can be expressed as its decimal expansion. You're already aware of representing rational and irrational numbers on the number line. The decimal expansion of a real number helps us to represent it on the number line. Let's represent 0.6 bar on the number line. Here, this decimal expansion is non-terminating recurring, where the digit 6 is repeating itself. we know that this decimal lies between 0 and 1. Let's look at the section closely by using a magnifying glass. We divide the section into 10 equal parts. Now, we'll represent each part as shown. On observation, you can notice that this decimal expansion lies between 0.6 and 0.7. Let's again look at the section closely. We again divide the section into 10 equal parts and represent them as shown here. Now, you might locate this decimal expansion between 0.66 and 0.67. Again, focus this section on the number line. Let's divide the section into 10 equal parts again. Represent these parts as shown. Now the decimal expansion lies in this section of the number line. Let's magnify the section and observe closely. Next, divide them into 10 equal parts and represent them as shown. Now, you can locate the decimal expression in this section of the number line. If we keep on continuing this process, then the degree of accuracy will be more. This process of visualization of representing a decimal expansion on the number line is known as the process of successive magnification. Similarly, we can also visualize a non-terminating, non-recurring decimal expansion on the number line. Based on this visualization, we can conclude that every real number can be represented on a number line uniquely. Let's recap. The collection of real numbers is the collection of all rational numbers and irrational numbers together. It is represented by the capital letter R. A real number is either rational or irrational. A rational number can be expressed as its decimal expansion. In case of division, if remainder becomes 0 after a certain stage, then the decimal expansion is terminating. If the remainder never becomes 0 but repeats after a certain stage, then the decimal expansion is non-terminating recurring. The decimal expansion of a rational number is either terminating or non-terminating recurring. The decimal expansion of an irrational number is non-terminating non-recurring. There are infinitely many irrational numbers between two rational numbers. Every real number can be represented on a number line uniquely. Welcome to the lesson on operations on real numbers. At the end of this lesson, you will be able to perform different mathematical operations on real numbers, represent the square root of a real number on a number line, and list the identities related to square roots. You will also be able to rationalize a number whose denominator is an irrational number. A real number is either a rational number or an irrational number. When we add, subtract, or multiply two rational numbers, we get a rational number. Even when we divide one rational number by a non-zero rational number, we get a rational number. This implies that rational numbers satisfy the closure property under these operations. But this is not the case with irrational numbers. Let's have a look. On adding 3 plus the square root of 2 and 3 minus the square root of 2, we get 6. On subtracting the square root of 3 from the square root of 3, we get 0. Similarly, if you multiply the square root of 2 by itself, then you get 2. If you divide the square root of 3 by the square root of 3, then the quotient is 1. Here in all the cases, the obtained results are rational numbers. Thus, irrational numbers do not satisfy the closure property under these operations. Also, real numbers satisfy the commutative, associative, and distributive laws. Let's recapitulate them quickly. The commutative law states that numbers can be added or multiplied in any order. The associative law states that in addition or multiplication numbers can be grouped in any order. The distributive law involves both addition and multiplication of numbers. What do you get if you add or multiply a rational number with an irrational number? We know that the square root of 5 is an irrational number. That is, the decimal expansion of the square root of 5 is a non-terminating, non-recurring. On adding this non-terminating, non-recurring decimal to 3, we get a non-terminating, non-recurring decimal. Similarly, on subtracting an irrational number from a rational number, we get an irrational number. Thus, we conclude that the sum or difference of a rational number and an irrational number is an irrational number. On multiplying the square root of 5 by 3, we get an irrational number. Similarly, on dividing a rational number by an irrational number, we get an irrational number. Thus, we conclude that the product or quotient of a rational number with an irrational number is an irrational number. Can you represent the square root of a real number on a number line? First, let's consider the square root of 4. We know that the square root of 4 is 2. OA represents the square root of 4 on the number line. Now, can you represent the square root of 2.2 on the number line? To determine its position on the number line, we first find the value of the square root of 2.2. We'll find it geometrically. First, we'll mark the distance 2.2 on a line. Let's represent this distance as AB. Next, we mark a distance of 1 unit from B and represent the point as C. Let's represent the midpoint of AC as O. Now, we draw a semicircle with the center O and the radius equal to the measure of OA or OC with the help of a compass. We draw a line through B perpendicular to AC with the help of a protractor. Let the intersecting point of the semicircle and the perpendicular line be denoted by D. The distance BD is the square root of 2.2. To represent the square root of 2.2 on the number line, measure the distance BD with the help of a compass. Mark an arc OE equal to BD on the number line. Thus, the distance OE represents the square root of 2.2 on the number line. Similarly, we can represent any positive real number, x, on the number line by finding its value geometrically. You can perform this by taking a point B such that AB is equal to x. Then, the distance BD is equal to the square root of x. This result can be verified by using the Pythagoras theorem. Let's join the points O and D. Here the triangle OBD is a right angle triangle. Now OD is equal to OC, which are the radii of the circle. Since O is the midpoint of AC, OD is equal to AC divided by 2, which is equal to x plus 1 divided by 2. Now OB is equal to AB minus OA. Substitute the values of AB and OA. Let's simplify this. Thus, OB is equal to x minus 1 divided by 2. Applying the Pythagoras theorem on triangle OBD, we have OD square is equal to BD square plus OB square. This can also be written as BD square is equal to OD square minus OB square. Let's substitute the values of OD and OB in this equation. Let's simplify this. Thus, BD is equal to the square root of x. Therefore, we can conclude that the square root of any positive real number exists. Identities related to the square roots are useful to simplify numeric and algebraic expressions. Here A, B, C and D are positive real numbers. The first identity is the square root of AB is equal to the square root of A multiplied with the square root of B. Let's verify this with the help of an example. Here the square root of 4 multiplied with 9 is equal to the square root of 36, which is equal to 6. Similarly, the square root of 4 multiplied with the square root of 9 is equal to 2 multiplied with 3, which is equal to 6. Thus, both the sides are equal. The second identity is the square root of A divided by B is equal to the square root of A divided by the square root of B. Let's take this example. The left-hand side of the example is the square root of 16 divided by 4 equal to the square root of 4, which is equal to 2. Similarly, on simplifying, the third identity is the product of the sum and the difference of the square root of. Let's verify this. Now, simplify the left-hand side 3 minus 2, which is equal to 1. Thus, both the sides of the exact root of b multiplied by a minus the square root of b is equal to 9 minus 2, which is equal to 7. Thus, both the sides. Then, expand the expression. Let's simplify this by using the first identity. Let's first consider the left-hand side of the example. Now we expand this expression. Apply the first identity and simplify this. This is equal to the right-hand side of the example. By now, you can also represent them on a number line. Can you visualize 1 divided by this with the square root of 5? Then the product is rational. Now, this is the equivalent expression, where the denominator 5 is the rational number. Now, we can easily represent this on the number line. This lies between 0 and the square root of 5. Let's recap. The sum, difference, and the product of two rational numbers is always a rational number. The quotient of a division of one rational number by a non-zero rational number is a rational number. Rational numbers satisfy the closure property under addition, subtraction, multiplication, and division. The sum, difference, multiplication, and division of irrational numbers are not always irrational. Irrational numbers do not satisfy the closure property under addition, subtraction, multiplication, and division. Real numbers satisfy the commutative, associative, and distributive laws. The sum or difference of a rational number and an irrational number is an irrational number. The product or division of a rational number with an irrational number is an irrational number. Here are the identities involving square roots. The process of converting the denominator into a rational number is called rationalizing the denominator. Welcome to the lesson on laws of exponents for real numbers. At the end of this lesson, you will be able to apply the laws of exponents to real numbers. The collection of rational numbers and irrational numbers together make up the collection of real numbers, which is denoted by R. We note that mathematical operations such as addition, subtraction, multiplication, and division can be applied to the collection of real numbers. Can we apply the laws of exponents to real numbers? Let's verify the first law. Consider the term 2 raised to the power of 5. Here, 2 is called the base and 5 is the exponent. This term can also be written as 2 multiplied 5 times. Now, let's multiply the term with 2 raised to the power of 2, which is equivalent to 2 multiplied 2 times. The product obtained is equal to 2 raised to the power of 7. Can you see the relationship between the exponents of the three terms? Yes. The exponent 7 is equal to the sum of 5 and 2. Let's consider another example. Here, 2 are the two bases with exponents 2 upon 3 and 1 upon 3. Now, let's simplify it. Based on these examples, we can generalize the first law of exponents. This law states that when multiplying two numbers that have the same base, you can add the exponents. Here A is real positive number. M and N are rational numbers. Next, let's verify the second law of exponents. Consider another example. Here, we are dividing two exponential terms. The numerator and the denominator can also be expressed as follows. On simplifying, we get. Do you see a relationship between the exponents? Yes, you're right. 5 minus 3 is equal to 2. Let's apply the observation of this example to simplify another example. Based on these examples, we can generalize the second law of exponents. The second law states that we can divide two numbers with the same base by subtracting the exponents. Here A is a real positive number. M and N are rational numbers. Consider another example. This can be written as follows. On simplifying, we get the result as 1. Now, let's verify this example again by applying the second law of exponents. If we equate the solutions obtained by both methods, we get the following expression. Based on this result, we arrive at another generalization. Any non-zero real number raised to the power of 0 is equal to 1. Let's move on to verify the third law of exponent. Consider the next example. Here we have two terms, 2 raised to the power of 5 upon 2, the whole raised to 2, and 2 raised to the power of 5. Can you see a relationship between the exponents of these two terms? Let's examine the first term. Applying the first law of exponents, we can express this term as follows. On simplifying the first term, we arrive at the fact that the two terms are equal. This implies that if an exponential term is raised to an exponent, then you can multiply both the exponents. Based on this example, we can generalize the third law, which states that to raise a power to a power, just multiply the exponents. Here a is a real positive number. M and n are rational numbers. Let's verify the fourth law of exponents. Consider this example. Let's consider another example. The exponent 2 upon 3 is common. Hence, we can multiply the bases. The answer is 15 raised to 2 upon 3. The fourth law of exponents states that to multiply two numbers with the same power, raise the product of the bases to the same power. Here, a and b are real positive numbers and m is a rational number. Similarly, two different bases with the same exponent can be expressed as follows. This is the fifth law of exponent. The fifth law of exponents states that to divide two different numbers with the same power, you can raise their quotient to the same power. Consider this example. Here, we have to divide two exponential terms, 7 raised to 2 and 8 raised to 2. The exponent 2 is common for both the terms. Therefore, this can be expressed as 7 upon 8 raised to 2. So far, we have seen examples where the exponents were all positive rational numbers. Can the exponent be a negative rational number? To verify this, let's consider an example. Applying the second law of exponents, this expression can be written as follows. The answer is 7 raised to minus 3. This can also be simplified as follows. On equating both the solutions, we get the following result. With this, we arrive upon another important generalization. Any real number raised to a negative exponent is equal to the reciprocal of that number raised to an equal, and m and n are rational numbers.